Ready when you are.
All right. Okay, welcome back. So this is a big moment because we're going back to the units in the Beauty and Joy of Computing, the BJC curriculum. But if you look at our timeline, it's May. We just finished taking the AP exam. The students are happy, it's over. Maybe they were scared, maybe they weren't, maybe they were oblivious, but they did it, okay? They submitted their digital portfolio with their performance tasks. They actually showed up in the multiple choice exam and answered the questions. It's all over, okay? So we still have a month left in the semester. What are we supposed to do? Some classes are watching movies, okay? My son's chemistry class, I think, is watching Black Panther. I don't know, vibranium is an element. Okay, whatever. Maybe they're doing that. We could do that too. We could watch The Matrix. We could watch Brave. Why Brave? Computer generated. The hair computer generated. That's amazing. Okay. Some classes are playing video games. I know an AP Computer Science Principles teacher who is actually a former professional video game player. So at this time of the year, he challenges his students and he tells them, "Hey, we'll play video games. I'll play against you. If you beat me, you get an A in the class." He has yet to be beaten. He doesn't tell them that he used to be a professional video game player. He lets them choose the game. They're so confident, right? And he destroys them. So that's something else we could be doing. We could do any of those. If you do those, I'm not going to be upset. Okay, I understand. But what I like to do is I like to just have fun with programming, right? There's no pressure. They don't have to, quote, learn something new. They don't have to be graded, okay? This is just for fun. So Unit 7 is called Fractals and Recursion, okay? So it's got a few labs that kind of teach the idea of recursion and also introduce them to fractals, different kinds of fractals. Students can love this, okay? So when I say we could have fun with this, I'm really serious, right? Sometimes this will be the first exposure to fractals for students, and that is just lovely, okay? Because it completely changes the way you think about the world, and you're kind of like, wow, okay? I wasn't expecting that, okay? So for example, what exactly is the length of the shoreline in New Jersey? I'm sure you can go to Google and find out, okay? But the truth is that that is an approximation, right? Just how closely are you looking at the boundary between the sea and the, well, quote, dry land on the beach. If you look really closely, those estimates can actually keep going up and up and up as to what exactly is the length of the shoreline. That's a fractal happening, okay? So anyway, the first fractal that they will build is a tree, okay? And a tree, and this is what makes it a fractal, is kind of like self-referencing. So if you look at a tree, it has branches, but if you look at one branch just by itself, it actually looks like the entire tree. Okay, that's the idea behind fractals. Okay, so here's a very high-level strategy for building a tree. What we'll do, if you tell me to build a tree starting in this position, first I'm gonna like move to a different spot, right? If you think about it, that's like drawing, the stem of the tree or the principal branch of the tree, and then I will perhaps turn around this way and draw a tree over there. I'll come back, I'll go back this way, I'll draw a tree over here, come back, and then walk back so I end up exactly where I started, okay? That is recursion, because you see what I did twice there in the middle. I said, and then I'll draw a smaller tree over here, and then I'll draw a smaller tree over here. So to draw a tree, what do? I move around a little bit, then I draw another tree, move around a little bit, draw another tree, go back to where I started. That's recursion, okay? So that's the kind of thing that they do in this lab 1. And what's really nice is that it's a very, very gradual ramp to get them to kind of understand this. Take a look at this lab. I think you'll learn a lot. And like I said, we're having fun. So, don't stress, don't panic, don't try to get a perfect tree. Just kind of see what happens, okay? Now, a lot of people are kind of genuinely afraid about recursion. And it's possible that psychologists will discover one day that it's like snakes, right? If you're a baby and you see a snake, you panic, right? It's just built in. It's not learned behavior, right? Maybe recursion is like that. If you show recursion to a baby, they start crying, okay? And we don't outgrow that until we're like advanced computer scientists or something. So a lot of times people are really scared about recursion. So I would like to convince you, and I want you to convince your students, that recursion is actually very natural. So let's try it, okay? Let's think of writing a program that will sort all the elements of a list. What do I mean by that? I want the smallest one in the front, then the next smallest one, the next smallest one, and so on, all the way to the biggest one at the other end, okay? So how can we do that? Here is an approach. You give me a list. Let's suppose that that list has only one thing in it. Hey, guess what? It's already sorted. It's only one thing. That's the smallest, right? Okay, that was easy. Now, what if he has lots of things in it? I'll take one of the elements in the list. Maybe the first one, maybe the last one, maybe one in the middle. Doesn't matter. Pick one of the elements on that list, right? Find everything that is smaller than it. Put it on this side. Find everything that is bigger than it. Put it on that side. Okay. Now, sort all of the small ones. You see, we're running a routine to sort. I'm calling it, right? Sort all of the small ones. So now those are in order. Then put the one that I used to split. Then sort all the big ones. Put those in the end. Beautiful, right? The smallest ones are sorted, right? Those are all smaller than the one that I split on, and are smaller than the big ones, so they're in the right place. Then the one that I split on, which is smaller than all the big ones, and then the big ones in order. That's got to work, right? This little algorithm is called Quicksort. It's also called partition sort, okay? Different books, different names. The guy who wrote it is Sir Anthony Hoare, actually Charles Anthony Hoare, but he likes to be called Tony. And he really is a knight of the British realm. He is the only computer scientist I know who is actually a knight of the British realm, so it's really kind of cool. But he invented this, and when he invented this algorithm, he actually did it not recursively. And he shared it with people, and he called it Quicksort because it's really, really fast, okay? And people said, but it doesn't work. And it's like, of course it works. Look, I've wrote a proof and everything. They said, I don't see how it works. I don't believe it works. So he went back and he did a second paper where he described it the way that I just did, using recursion. And everybody was like, well, of course that works. That's the simple, my God, that's actually fast. You wouldn't think that. That's the power of recursion, okay? If you use it correctly, if you use it in the right places, it actually makes life so much simpler, okay? Now, when I talk to students and when I try to introduce this, right, like I said, I know they're skeptical. So sometimes I talk to him in this vein. I said, you remember Algebra 1, right? We gave you an equation like 2x minus 4 is equal to 7, okay? And then we said, find x. And Algebra 1 is all about finding x, okay? And there's things you can do, right? And then there's others like, 2x squared minus 3x plus 10 is equal to 5. Find x, right? And so they know what that means, right? And I said, all right, so let's do it again. But now what I'm going to do is I'm going to give you equations that don't have x, they have a function. And what I want you to do is find the function, find f, okay? So look at this equation right here. F of x is equal to, there's actually two parts to the equation. That's not uncommon, right? Like absolute value is minus x if x is less than 0, x if x is greater than or equal to 0. It's just definition by cases. So the first case is x is less than 1, f of x is just 0, okay? If x is greater than or equal to 1, okay, then f of x is 1 plus f of x minus 1. That's f. It's just, and you see that this is not a definition. This is an equation, right? Is it enough to figure out what function I'm thinking about, okay? Actually, that's a trick question. If I tell you that x has to be a non-negative number, then I have given you enough information, okay, to uniquely identify one function that has those properties that makes that equation true. It's like finding x when you say 2x is equal to 4. There's only one choice of x that works. Okay, there's only one choice of f that works if we're saying that x, the values that it works on, have to be non-negative reals. Okay, go ahead and try to figure out what the function is. I'll tell you at the end. Okay. By the way, I've had students actually, not all students, but I've had students look at that and go, "Oh, isn't that blank?" And they're right. Okay. So again, I'm trying to get them to understand that what I'm doing is I'm using equations, equalities. This is equal to that. Left-hand side equals right-hand side. That are true and that you can recognize are true. And then eventually, maybe I have enough equalities that the function is uniquely determined. So that's like programming. Here's the function I want you to compute. So this is beyond what the mathematical prerequisite is for this class. Okay, the mathematical prerequisite is Algebra 1. This is actually pre-calculus. Okay, but I find that oftentimes students actually have that, and so it's okay to have a little side lecture, really just for those students, and the rest can play along. Okay, so here are 6 equations that I think all these students will agree. The sine of minus x is equal to the sine of x. I think they'll say, yep, I know that. That's a true fact. That is an equation. The sine of 0 is equal to 0. They'll say, yes, that is a true equation. The sine of 2x is 2 times the sine of x times cosine x. The double sine formula. They'll go, yeah, I remember that. I believe that's true. Okay, we're losing them a little bit, but that's okay, right? The cosine of minus x is the same as the cosine of x. Yep, they remember that. Cosine of 0 is equal to 1. Yes, that's true. The cosine of 2x is cosine squared of x minus sine squared of x. Yeah, I believe that's true. I kind of remember that. I mean, a lot of students that I've met, they remember the first couple of formulas. They have a hard time with the other ones, mostly because they haven't seen that those are useful in a lot of contexts yet. So, they don't quite memorize them, and that's okay, right? But they'll agree that those 6 are really equations. So then what I tell them is, okay, let me collect those equations like this. Sine of x is equal to the sine of minus x if x happens to be negative. Okay? Is equal to x if x is really small, say between 0 and 0.01. You could say between 0 and 0.00001. Okay? Right? Point is really small. By the way, we said the sine of 0 was 0. Now I'm saying the sine of x is x. That's a little bit different than the equation that we saw in the previous slide. But perhaps the students will agree that sine of x is actually equal to x when x is really, really small. Okay? So I prefer that. It's a better approximation. Okay? Now, the sine of x is equal to 2 times the sine of x over 2 times cosine x over 2. You see, that's that double angle formula, right? Okay, all right. So that's great, except we call cosine. But don't worry about it, because here's cosine. Cosine of x is the same as cosine of minus x if x is negative. Is equal to 1 if x is really, really small, right? And it's equal to cosine squared of x over 2 minus sine squared of x over 2 otherwise. This you could actually use as a recursive definition of sine and cosine. Okay? By the way, I designed 2 functions for the price of 1. These 2 functions are recursive in terms of each other. This is even fancier than recursion. This is mutual recursion. And it's using equations they already know, or at least they can remember if prompted. Okay? So that's the message that I try to give them, is you see, you've actually been doing this kind of stuff forever. Maybe you just didn't realize it. Okay? But we've written equations like e to the x plus y is equal to e to the x times e to the y. That's actually using e to the x on both sides, right? Can you do that? Yes, of course you can. Just like you can write an algebraic formula that has x in both sides of the equation. That's okay. Then we move them to one side to solve, right? That's what I'm trying to get across, because I'm trying to remove some of this mystery of these recursive calls. Okay, let's look at Lab 2. Okay, Lab 2 is just a collection of projects that use recursion. What's the point of these? Students should just pick 1 or 2 or whatever and play with them, right? Maybe they'll build the triangles there, or maybe they'll build a funny L curve, or the Coke snowflake. I love the Coke snowflake. Or maybe they'll go into even cooler looking trees than what we did earlier. Maybe they'll decide to do abstract art, okay? They do all sorts of things, all of which are using recursion. That's the point of that section. So what I like to do is I like to tell the kids, hey, remember, the AP exam was last week, right? So we don't have to stress about that. Just have fun with this and build something cool, okay? Next week, towards the end of next week, we'll get together for our last lecture, and we can show each other some of the cool things that we built, okay? Think of it like a gallery exhibition, right? That's really the way I like to approach this part of the course. Okay, so that's it for Unit 7. So Unit 8 talks about recursive and higher order functions, okay? Unit 7 was about recursion in general. This is about recursive functions, okay? So the first thing that they do is they talk about the recursive reporters. A reporter is just a snap language slang for function, okay? And they talk about when can we actually write functions using this recursion idea. So here's a function that they do. It's supposed to find how many segments there are in a tree. Remember, we built these trees by repeatedly calling the build tree function, or procedure, I should say. And now we're actually trying to say, well, so how many little pieces are there? This is a function that computes it. And the answer to the question, when are you allowed to do that, is when your function can be written in cases, and the function is consistent. And what do I mean by that? If there's two different cases that apply to the same input, the same value of x, then both should actually return the same value. So for instance, absolute value of x. If x is less than or equal to 0, then it's minus x. If x is greater than or equal to 0, then it's x. Notice that both cases apply to x equals 0. But it's OK, because minus 0 is the same as 0. It's just 0, right? So it's consistent. Okay. What you don't want is something that says, like, the sign of x is minus 1 if x is less than or equal to 0, plus 1 if x is greater than or equal to 0. So when x is 0, it's minus 1 or plus 1. That can't be right. That's not consistent. So that's the first C. Okay. The second C is that it has to be complete. So if you write your function, and then I say, OK, so what's the value of f of 0? And I go through the cases. Nope, doesn't apply to 0. This doesn't apply to 0. I don't know the value of 0. Then I made a mistake, right? I want it to be complete. So at least one case applies to some input that I want to pass in. And finally, it needs to be computable, right? That's actually the subtle C. You may remember from a previous unit that we talked about that some problems are actually undecidable. You cannot solve with a computer. One of those is this program on this input will terminate. Remember that, the halting problem? Well, that's what we mean by computable. What we mean by computable is that you give it some input, it will terminate, okay? So we can't guarantee computable, right? So what we do is we pick special cases where computable is obvious. So for example, the segments of n is equal to, and that depends on the segments of n minus 1. So notice that n, the value of n, keeps getting smaller, right? And eventually we get down to 1, if you give it a positive integer to start with. So it stops. So yes, it terminates. Yes, it's computable, right? That's really the kind of argument that we try to refer to, okay? So in here, this snap code is actually equivalent to this function definition using the notation we used earlier. The segments of n is, by cases, if n is equal to 1, then just 1. Otherwise, it is 1 plus 2 times the number of segments in a tree of size n minus 1. Because remember, we built a tree of size n minus 1 over here, and then 1 over there. So we need twice the number of segments, and then we connected them. That's the 1 plus, okay? So that's recursive reporters, okay? Now, the second thing that they want you to do, the second lab, is about sorting a list. So here's a list. I want to convert it into a list that's in order, okay? They're simply teaching the idea of recursing down a list. And they do it in two ways. Selection sort, which is pick the smallest element, put it in the front, and then recursively sort the rest of the elements. Puts the smallest one, puts it in the front, which is now position 2, and so on and so forth, okay? So that's selection sort. And then partition sort, which is the one I talked about earlier, that actually splits the list based on some random element, the small ones, the big ones, and then sorts each one of those recursively. After that, we have projects, okay? Again, this is just an opportunity to show off. So for example, one of the projects, the first one they suggest, is Pascal's triangle. I kind of like Pascal's triangle simply because it's a connection to stuff they did in Algebra 1, right? So that's kind of cool, right? It's binomial theorem, that kind of stuff. They have lots of other little projects. Like, for example, how many sets does a set of size 4 have? Okay, that's a question. By the way, the answer is 16. That's a question, right? And they can go off and try to answer that by writing a program that actually counts them all. Okay, so again, that's a recursive program. Okay, after that, then we look at higher order functions, which is the other half of this. Now, a higher order function is just a function that accepts an argument that happens to be a function. We have seen those already. We saw keep all the elements of this list that pass this test. We saw map this function over each element of this list. Okay, we saw those earlier. So now what we're going to do is we're going to write higher order functions. Okay, there's only one thing that they have to learn that's kind of special, which is how to tell Snap that what I expect to go in this argument is a function as opposed to the value that that function evaluates to. Okay, that's called ringifying the argument. I don't know why it's called ringifying. That's just what they called it. Okay, but that's the only new thing here. And they're basically asked to write map and keep, which they used earlier, so they already know kind of how they behave. Okay, so that's the end of the section, right? I can't help but end with this Escher painting that actually does recursion, right? But it's the kind of recursion that makes people nervous. So I understand why they get nervous. This simply couldn't happen if you did the 3 C's because it wouldn't be computable. The arguments aren't getting smaller, okay? And before I go, I promised I was going to tell you what that original function was that had f of x is equal to 0 if x is less than 1, f of x is 1 plus f of x minus 1 if x is greater than or equal to 1, okay? And that is the floor function, okay? So it's a function that the students know since perhaps middle school. Maybe they never saw how to define it, right? They just simply know what it does. And now they can actually see a definition. They could add it to their code if they wanted to, just like sine and cosine, which we did. All right, that is it. That is the entire APCS Principles course. I hope you learned a lot. And I really hope that you teach this course in your school next year, or at least very soon. Thank you.